So yeah, so we were talking about these things. So yeah, so if you have a random variable, then we have its entropy. And if you have two random variables, x and y, with some joint distribution, then we can think of this as a common entity, and it has its own entropy. But if you subtract the entropy of x from the entropy of xy, what you get is defined to be the conditional entropy. And last time we massaged this expression and realized that this conditional entropy is actually an average. So you take the values of x. There are various choices for x. And then once you have a choice for x, the distribution of y becomes the conditional distribution. And that I call y subscript x. For a particular realization of capital X, you get an entropy here, and you take the average of those entropies. And that is actually an alternative definition of conditional entropy. Okay, so, and then there was this expression which we defined to be mutual information. And the reason it is called mutual information is that it sort of reminds us of the Venn diagram, in the sense that, I mean, this is a completely bogus analogy, by the way. But so this is the information of x, this is the information of y. So what is common? Well, you take the full area and, sorry, take this fellow's area, and then subtract the union or something like that, like the inclusion-exclusion formula in combinatorics. Okay. So, but this mutual information we saw had a central role in communication over a noisy channel. I was sort of beating about the bush last time. So let me just tell you what a noisy channel is and what Shannon's theorem is, and how this expression determines the capacity of the channel. It determines how much information you can communicate when you have a noisy channel. Okay. So what's a channel? Well, a channel is just an object like this, into which you feed a symbol from an alphabet X, and out comes a symbol from the alphabet Y. And what you're given here are these, this is called the characteristic of the channel. That is, if you feed X, what is the probability that a particular Y will show up on the outside? Okay. And you're trying to use this channel for communication. And how do you use this channel? You have been given a particular message, let's say a word, W, in 0, 1, and then you encode it and into a word, a code word, and this you pass through this channel, and this word comes out as something else, and then you decode. And you get a word W prime. So this encoding and decoding, these are algorithms which you design, okay? And this particular encoding decoding algorithm takes n times r bits and converts it into words which have n symbols for this channel, okay? So in this case, we say that we are communicating at rate r. Yeah? For every n uses of the channel, we are sending nr bits of information. So the rate is NR divided by N, that is R. Okay. Now, what are the goals? The goals of designing all this. One is we want this probability that W equals W prime to be large. We would like, as engineers, to have a reliable communication system so that when you try to send some bits through this, in the end, what you receive, what the decoder finds out, is what was intended. And the second thing is, we want to maximize. And suppose you're given these characteristics, and we can assume that this N is large, yeah, for very large N. So given a channel, you would like to know what is the best encoding scheme and the best decoding scheme, or what is the best encoding-decoding pair that achieves this, yes? And the answer is given by Shannon's theorem, okay? And let me tell you what the theorem was. So, yeah. So there is something called the capacity of the channel. And in defining this capacity, this expression will be used. So what is a capacity? You maximize over all distributions P, yeah, on, so P is a probability distribution on the input alphabet. Now, let us say X is a random variable which is distributed according to P. Now, the moment you have X, you sort of automatically have a notion of a Y. That is, if you were feeding something into this channel according to this distribution P, then something will come out and, yeah. Let me just say, so this is with N uses of the channel, but if I use the channel only once and fed X into it, which X? This X, out will come a Y, and X and Y will be correlated, yeah, depending on how this behaves. So we now have a Y, which is distributed, let me just say, according to the channel. Yeah, yeah. I'll erase this. Yeah, so X and Y are compatible with this channel. And so this is an optimization problem. Find the best P so that when you feed symbols into the channel according to P, the Y that comes out has as high mutual information as possible. Okay. And then the theorem says that, yeah, so the theorem has two parts. So I'll write something here, but before. So if R is less than the capacity of C, yeah. So yeah, this is a capacity, and you should just accept the intuitive meaning of the word capacity. If you're trying to communicate at a rate R less than capacity, then you will succeed. If you try to communicate at a rate greater than capacity, you will fail. Okay? That is the spirit of this theorem. Let us see how we write it in mathematics. Yeah. So if R is less than capacity, then there exists encoders which takes 0, 1 to the power nr and a decoder. So that is, there is a function encoder which takes this, and a decoder which would go from such that probability that W is not equal to W prime so you can specify delta. You say, I want error probability 0.000001. Okay. Then I will tell you the n, and then you will start encoding R times n bits, yeah, into n symbols for the channel. And when the decoder comes, decoder applies it to the output of the channel, it will obtain a W prime. No, R will be, depends on the channel. I mean, let us say, suppose this was, yeah, so let's say R is less than n1, but it depends on the channel. Yeah, but yeah. You would like to send, for each time you use the channel, somebody charges you 1 rupee. Okay? These are the outcomes of the experiment in your lab. How many outcomes of the experiment can you just send for 1 rupee? Okay? So if you can send more, it is better. Is that okay? So what this says is that as long as your aspiration is below capacity, okay, you will succeed. Yeah. But if you want to reduce your probability, you will probably have to perform a lot of experiments and encode them in bulk. You encode them in bulk. Yeah. So that is why for all large enough n. Okay. And what does, but this is just one part, and it is the converse exists. If you attempt to communicate at a rate bigger than capacity, then the probability that W will be not equal to W prime will actually become 1 minus delta. That is, you will, yeah. So this is true for all W belonging to 0, 1. Once again, let me explain this quantifier. No matter which message you want to send across, you can use this encoder and use this decoder. Which encoder? This encoder and this decoder, which is promised by this part of the theorem. Then, no matter which message you want to send, the output will agree with the input with high probability. The probability that it disagrees will be less than delta. And the part B, if R is greater than capacity, then no matter how hard you try, so instead of there exists, I will write for all encoders. Yeah, so I'm not, yeah, and decoder. There exists a W belonging to such that the probability that W equals W or yeah. So if you try to communicate at greater than capacity, there will be messages, yeah, which will be wrongly decoded with very high probability. 99% of the time when you try to send that message, the person at the other end is going to decode it as something else. Okay. So see, and this notion of mutual information is what tells you. Yeah. So now if this is capacity, if you're communicating at a rate less than capacity, your probability of error is, as n tends to infinity, your probability of error is 0. At capacity, things happen depending on the channel. But the moment you go beyond capacity, as n tends to infinity, your probability of error, worst case probability of error becomes 1. Okay, so there is this, yeah. So we saw a similar picture last time, that was for compression. For communication over noisy channels, a similar picture arises, but the threshold here is capacity. And in the definition of capacity, this information theoretic quantity, mutual information, comes into play. Okay, so that's all I wanted to say. Yeah. What are we doing? So maybe we'll, yeah. So the plan is maybe so let me just review one more thing. Last time we had this channel, the binary symmetric channel. So this is called the binary symmetric channel with error probability epsilon. What does this channel do? When you feed it 0, it sends, what did I do? So when you feed it 0, it comes out 0 with probability 1 minus epsilon. Now, we want to know the capacity of this channel. So somebody gives you a telephone line which has this property. You feed it 0, it doesn't always produce 0, but it produces 0 with probability 1 minus epsilon, 1 with probability. How are we going to use this channel? What is the best way? The theorem tells us, but the theorem tells us once you are able to compute this. What is the best input distribution, yeah, that you can think of here, which, so that the mutual information is as high as possible, okay? So, yeah, it will need a little bit of playing around, which I won't do, but assume that P is half-half. That is, it feeds 0 with probability half, 1 with probability half, okay? So then what is the joint? Yeah, so let's say X is distributed according to P, and Y given X is distributed according to the channel. Then what is I of X colon Y? Okay, so you remember I of X colon Y can be written in many ways. H of X minus H of maybe Y, sorry, X. Maybe I should do it the other way. Yeah, you remember many of these, all of them are mutual information. H of Y minus H of Y given X, H of X minus H of X given Y. Yeah. Okay, so if you feed 0 and 1 uniformly here, what do you think the output will be? What's the distribution of the output? If you feed 0 with probability half and 1 with probability half, what is the probability of getting a 0 on the output? Half times 1 minus epsilon plus half times epsilon, half. Yeah. So if you, that's why it's symmetric channel. Yeah. So if you feed inputs with uniform distribution, the output is uniform distribution. So what is this quantity? Yeah. If it is uniform distribution, it's 1. Yeah. Half. Sorry, my logs are all to the base 2. Huh? All right, and what is this? So what is the definition? There was a little tree that I drew. For each choice of X, I have to find out what is the residual entropy in Y. So if I feed 0, what is the entropy of Y? If I tell you that the input is 0, how much entropy does Y have? Sorry? It is a random variable which takes the value 0 with probability 1 minus epsilon and 1 with probability epsilon. Yes? So it is 1 minus epsilon log plus epsilon, yeah, which we call little h of epsilon. Yes? So that is when you feed 0. And when you feed 1, what is the entropy of Y? Conditioned on x equals 1. Yeah, it just flips, but it is the same number. Yeah. So the average of these two numbers, yeah, so average of two numbers which are the same is the same. So this quantity, okay. So the capacity of the binary symmetric channel is 1 minus h of epsilon. Okay. So if you're trying to okay, so let's just do some sanity check. So if epsilon is 0, yeah, if epsilon is 0, that means the channel is perfect. You feed it 0, produces 0. Yeah, if you give it 1, it produces 1. In that case, you can communicate at the rate 1. Yeah. Now, if epsilon is half, yeah, if you feed it 0, output will be 0 or 1 with probability half. Yeah, that means it is completely forgetting the input. Now, if you have a telephone line like that, I have one. Yeah. So, yeah, so you feed it a 0, and it will give you 0 or 1 with probability half. Then how much can you communicate through this? 0. And nothing can be communicated, like, because no matter what you send, only noise is coming out at the other end. Okay. In that case, this becomes 1. Yeah. Now, last time we had one more channel, the binary erasure channel. I'll let you compute the capacity of that channel. Okay. So yeah, maybe tomorrow's tutorial we can think about it. Good. So this is what I wanted to say yesterday. Okay. So let me move to the new topic, which I really wanted to do today, is the application of information theory in combinatorics. And we will see 3 examples today. Okay. But if you have any questions about Shannon's theorem and the various entropy quantities, we can discuss it. So I'm erasing this. So 2 things which I should have mentioned. So suppose there is a random variable x which takes some, yeah. So it takes R values with some non-zero probabilities, but all these have 0 probability. Then when will X have maximum entropy? Which distribution do you think is has the greatest entropy? So suppose you are allowed to take only R values. How should you divide the probability among these R values so that your entropy is as high as possible? Just intuitively, what do you think? Which is the most uncertain system? Uniform distribution, yeah. And in that case, what will each of these probabilities be? 1 by R. And then if you plug in 1 by R for all the probabilities in your formula, you will get yeah. Sorry. Yeah. Now, I don't know if you're familiar with this word support. Support means the number of elements that it takes with number of elements that have non-zero probability. So the maximum entropy that you can get is at most this. I will let you check this. So you have a formula, just find out for what distribution the entropy is maximum. Okay. And usually, since I've said everything, every inequality more or less follows from Gibbs inequality, just use the Gibbs inequality and try to get this fact out. Okay. Good. So, and equality if fine. So this is our first example. It's called the Loomis-Whitney inequality. What is this? So it's a bigger thing, but we are just going to do a baby version. So you have some points, set S of points, and there are n points here. Okay, so there are, in three-dimensional space, there are n points, n discrete points in 3 dimensions. And this is the z-axis. Sorry, I'm always a little confused. I think you people are probably particular about the right-hand rule. So, yeah, okay. So this is x, this is y, that is z. Okay, yeah. Okay. So now you project this n onto the xy plane, and you get, I'm writing n sub z because I projected in the direction z. Okay, and this n sub z may be different from n. Why? If you take some n points and project them, the number of different points you get may be different from the number of points that you've started with. Why? One point might fall on the other. Good. And then there is n sub y, and you project it on this side, you get n sub x. Yeah. So I've not written this down. So when you project this, you get n sub z points here, n sub y points here, and n sub x points here. And the Loomis-Whitney inequality says that n sub x times n sub y times n sub z, yes, is always. It could be that one of them is very small. If all the points were aligned on the z-axis, then n sub z in the direction of the z-axis, then n sub z would be 1. But then these will have to be large. All of them cannot be simultaneously small. Their product will always be at least n squared. Okay. So there are many ways to prove the Loomis-Whitney inequality. Yeah. But it will turn out that we can just not do anything and get the Loomis-Whitney inequality. So let me try to persuade you. Yeah. So this is a deterministic inequality, no probability involved. Okay. But we are going to prove it using information theoretic considerations. So what is a point? Yeah. So we are told that a point basically has 3 coordinates, x, y, and z. So it has 3 coordinates, x, y, and z. Now, if you project it onto this and somebody tells you this point, out of these 3 pieces of information, what do you get out of looking at this point? Yeah, you get x and y. And from this, x and z, yeah? And from this, y and z. So if somebody told you all 3 points, you are getting each piece of information twice. Now, information goes as log. So since you've got the information about this twice, it must be that this product must be n squared. Yeah, so that's the spirit of the proof, and let us just formalize it. That's the end of the proof, actually. Yeah, the amount of information contained in these 3 points is twice the information that the point contained anyway, because each piece of information has been provided to us by 2 sources. Yeah. So I can keep shouting louder and louder, and then, yeah. But yeah, how does one do the math? Yeah. So P is this, and you understand what is P sub Z? P sub Z is, so P sub Z is the projection. So pick P uniformly from S. Then it creates a certain distribution here. That particular point is called Pz. Okay, it may not be uniform. Certain points might have many points stacked on them. Other points may have fewer. A uniform distribution need not generate a uniform distribution. Okay, that P sub Z, P sub Y. P sub Y consists of, what should I write here? Yes, and P sub, what's the third thing? X. Yeah. Yes. Why is this true? Uniform. Yeah. When you have uniform distribution, the entropy is log of the number of possibilities. But this is the same thing as h of, yeah, because a point, after all, is 3 pieces of information. And whenever you see this, you write this as h of x plus h of, yes, it's called the chain rule, which is just repeated use of conditional entropy. Is this okay? H of x, y, z is h of x plus h of yz given x. But that yz given x can be replaced by y given x and then z given xy. Is everybody okay, yeah, with this? I'm just repeatedly using the rule for entropy, conditional entropy. All right. Now, h of pz, h of py, and h of px. Now, how many possibilities could pz take? Nz possibilities. So what can we say about the entropy of pz? Yeah, it is less than or equal to log of nz, because we don't know it is uniform, but it can never be more than log of nz. This can never be more than log of ny. This can be never more than log of nx. I hope everybody's okay this far. Yeah, good. And this one is h of, I'm just probably boring you now. Yeah, you know what I'm going to say. Let me expand. This is h of x plus h of, this is h of x plus, I'm writing it here. This is h of y plus h of nothing happened. Yeah. If I were to add these 3 rows, yeah, on the left-hand side, I will get log of nz, log of ny, log of nx. Yeah. Okay. Here there is one h of x. Here there are 2. Here there is one h of y given x. There is an h of y given x. And this is h of y, which is bigger? H of y given x or f h of y? Yeah, I mean, we spent some time last time to say that conditioning only reduces information. So this quantity is definitely dominates this. What about here? Both these quantities have this conditioning over x, but this has more conditioning. More conditioning means less information. So both these dominate this. Okay. So clearly, log of nx plus log of ny plus, sorry, I'm summing it in a different order, but yeah. So, I mean, while you admire this proof, I would also like you to think about if you didn't know this, how would you have tried to prove this inequality? That is, you have n points, you project it here, project it here, project it here. The product of these three numbers is always n squared. Okay. Now, there are many ways to prove this. It's one of, there is a book called the Cauchy-Schwarz Masterclass. Okay. So, which has all applications of Cauchy-Schwarz, and this is one of the celebrated applications of the Cauchy-Schwarz inequality. But it takes a little bit of thought to even apply it properly. But here, at least, I would like you to think that it was completely natural. Yeah, each piece of information is available from two sources. That is the only thing we have done. Yeah, and each piece of information that P contains is available from two sources. So this was my first example. Sorry, question. Yes, so actually, you can generalize it in many ways. So suppose you have a body in k dimensions, and you take its projection onto every k minus 1 dimensional coordinate plane. Yes, so now there will be k minus 1 dimensional volumes that are created on those planes. Yeah, and then if you take the product of those volumes, then it will be the volume of the original body to the power. Each piece of information is now available from how many sources? If, yeah, the only, when you project along the z-axis, the only piece of information that is lost is z. Yeah, so every piece of information is now available from k minus 1 sources. So you get to write k minus 1 here. Okay. Now you don't necessarily have to project them into k minus 1 dimensional subspaces. You take the n-dimensional body and take r of the coordinates and look at that r-dimensional subspace generated by those r coordinates and project it there, you will get an r-dimensional volume. The product of all these volumes, provided every coordinate participates in k or of them, you can write k here. So you just, yeah, whatever you think must hold, holds. So for some, this is all a special case of a general theorem in information theory, which goes by the name. I will add a reference in the notes, which is a survey on applications of entropy or information theory to combinatorics, and you will find this there. Yeah. So let's say this is an undirected graph G. There are n vertices, and each vertex has every vertex has D neighbors. So what's a walk in a graph? You start at a vertex, move to its neighbor, move to its neighbor. This is a walk of length r, provided each you're only allowed to walk along the edges. So here's a graph. Every degree is D. These graphs are called D regular graphs. So how many possible walks are there? How many such objects are there in this graph? This is an easy counting problem. So for V0, how many choices are there? You can start your walk anywhere. And then for V1? V1, how many choices? Only D, because you have to move to a neighbor. Yeah? Let me write this down. N times D to the power. So in a regular graph, yeah, if all degrees are R, the number of walks is exactly N to choose the starting vertex, and then you have D choices for each move. And the number of walks is N times D to the power R. So you have a graph with N vertices, but all the degrees are not necessarily the same. Okay. And let so you look at this graph, you start from a vertex and you start walking. Yeah. And the number of different walks is this. Okay. So now let us denote by D bar the average degree. Yeah, so please ask if something is not clear. So I'm now trying to study the same problem for an irregular graph. The degrees are not necessarily the same. I'm still interested in counting the number of walks. And the parameter with respect to which I want a bound is D bar. What is D bar? The average degree. So the theorem, yeah, so it is a little, yeah, so at this point, it's not clear which way it should go. Yeah, that is, there might be vertices that are of high degree. So you get a good number of possibilities when you go out of them, but their neighbors are of low degree. Yeah. So does this, yeah, so I would like to compare the number of walks is it greater than or equal to or less than or equal to? Okay. And it turns out that So what was here proved or obvious for a deregular graph? If you have an irregular graph, then the same sort of statement holds, but it's an inequality in this direction. It is n times d bar to the power. That is sort of, if you want to keep the number of walks small, the best thing for you to do is divide the degrees equally, yeah, among all the vertices. Yeah, individual degrees can be 5, 7, 0. 0 also is allowed. Yeah. Yeah. So when you, so, oh, my R is at least 1. Yeah. So if you land at a vertex of degree 0, then you cannot go. So it will not count as a walk of me. Sorry, thank you. Yeah. R is at least 1. So how do we deal with this? Yeah. And where is the probability? Yeah. So I mean, the message of these information theoretic, techniques in combinatorics is that even if the problem doesn't have probability, you have to impose probability on it and then start looking for information. Okay. So now you have a graph and which is not regular, yeah, and I want to do information theory. Yeah. So I want to impose a certain distribution on these walks. You've been tortured last week. So you can think of a random walk. So whenever you are at a vertex, and if it has 5 neighbors, you choose one of them with probability 1 over 5. Yeah. So let's do that. Yeah. So yeah, forget vertices of degree 1, so that whenever you are at a vertex, you have somewhere to go. Okay. Now, this has a transition matrix. Sorry, you multiply the transition matrix to the probability vector on the right in physics or on the left? Probability vector is a column vector? Yeah. Thank God. Okay, good. Very good. That's what I like. Yeah. I mean, I think the probabilists like to keep them as row vectors and then. So, yeah. So if you are at a current state, that is, you have a current probability distribution, you multiply it with the transition matrix, and you get where you will be at the next step. Okay. And if you have a vertex V, and its neighbors are this, 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 and this, on each of these other positions, you will write 0. And in these positions, what will you write? 1 divided by? Yes? Is this how you think? Okay, good. So this, yes, imagine this random walk being performed on the graph. Okay. So for this random walk, yeah. So if you take a graph, an undirected graph, and you think of this very natural random walk on it, what is the stationary distribution? That is the eigenvector with eigenvalue 1. Yeah. So every such Markov chain has a stationary distribution. I hope you've been told. And for this graph, what is the stationary distribution? Uniform on? So the vertices get importance depending on the number of vertices. So you have to give the probability in proportion of the degree. This is just a normalizing factor because the sum of the degrees in a graph, if you, sorry, is this, yeah, so I don't know if I'm insulting you by saying these things. So if you sum the degrees of the vertices in the graph, what is its relation with the number of edges in the graph? Twice. So the sum of the degrees is twice. So that's why I'm normalizing like this. Is that okay? Yeah. Okay. Is this something they should know, or it's okay? Yeah. So yeah, good. No, so that's a very nice thing. So it is detail balance because let us see. Suppose you are at a vertex V here and a vertex W here, and you have landed up at vertex V, and this happened to be a neighbor. How much probability flux goes in this direction? Degree V divided by 2 times E of G. What's the probability that after landing at this vertex, which happens with this probability, you would go to this vertex in the next step? Okay, this times, yeah, this is the probability of landing at vertex V, and this is the probability of making this transition. So what's the amount of probability flux, so to say, moving in this direction? I'm sorry, I'm probably using the word flux wrongly, but okay. Yeah, and that's okay. That's okay. Okay. Yeah. Oh, yeah, probability current. Okay. Yeah. Going in this direction, it is 1 upon 2e. And what is the flux coming in the other direction? Well, it didn't depend. The degree cancels. That means on each edge, if you start with this distribution, the amount of probability current going this way and this way are balanced. And that's what Sanjib called detail balance. At every edge, things are being exchanged in equal amount. So the total probability of this doesn't change once you apply this transition matrix. Okay, is that okay with everybody? Yeah. You probably know it in many ways. Yeah. Okay. Yeah. That's the sort of creative thing in the proof. The proof was, the statement that I wanted to prove was something like this. You suddenly start imagining a random walk in the graph. Yeah, and that random walk has a stationary distribution. All this you know from before, okay? And now we start doing information theory. So, yeah. So what do I mean by this? V0 is picked according to the stationary distribution pi. Yeah. So I'm considering this walk. So V0 was generated according to pi, and then V1 was chosen to be a uniformly, I mean, one of its neighbors. Then V2 was one of the neighbors of V1, and so on. Okay. And depending on their degrees, the probabilities involved will be different. But each time, the neighbors are chosen uniformly among the possibilities. Now, do you agree that this quantity this is distributed on the set of all walks? Yeah. So its entropy cannot be more than, yeah, be set somewhere. Yeah. A random variable cannot have more entropy than log of its support. Yeah. And the support of this walk is at most this. This okay? Yeah. And yeah, so I will expand this, but it turns out that it's somewhat easier to keep V0 and V1 together, plus h of V2 given V0 and V1. H of V3 given V0, V1, V2. H of VR given V0, okay. Nothing has happened. This is an equality. Yeah, I've just expanded this. Is everybody okay with this? Yeah. We will come to this. What does this look like? We started the walk in the stationary distribution. Okay. So if I look at the distribution, where did my VIs go? So V0, V1, V2. If I look at the distribution of VI, what is the distribution of VI? I start at the stationary distribution and take a walk. And I ask you, what is the distribution of the fifth vertex? If you start a process in stationary distribution and evolve it for 7 steps, what is the final distribution? I mean, that's why it's called stationary. Yeah. So the distribution of each of these VIs is the same as this distribution. Yeah. Okay. So you took some walk. There was a V0, sorry, you had a V0, V1, and so on. Yeah. And then you have landed up at, let us say, VI minus 1. And now you have some choices for VI. So how many choices would you have here? If you are at vertex VI minus 1, how many choices would you have? Degree of VI. And we have decided to put what distribution on them? Uniform. So what is, so there is the ith term here. Maybe I should have written the ith term. H of Vi given V0 to Vi minus 1. Then the last term, Vr given V0 to Vr minus 1. When you are at a certain vertex V, the number of choices you have is degree of V. And the entropy that is obtained by the next vertex is log of the previous vertex degree. So do you agree that each of these terms is actually summation over all V in the graph, degree of V divided by n times d bar? This. Two times Eg is also n times d bar, yeah, times you hit a particular vertex of the graph V with this probability. And when you hit that vertex with that probability, the next vertex has how much entropy? So the conditional entropy was the average of these entropies, average with respect to the distribution of Vi minus 1. So that is, now, I mean, the reason we chose this random walk and the stationary distribution is all these terms will be the same because we are in the stationary distribution. Okay. So basically, this term is equal to there are r minus 1 terms here. Okay. Let's continue. One reassuring thing is vertices which have higher degree are being given greater importance in this sum. Yeah. So again, the usual distribution. Now this log is a concave function. Yeah. So what happened here? So this is the average of the logs. So if I write log of the average, yeah. Why is it going in the wrong direction? Did I write my whole inequality wrong? Let us continue. Yeah. So which way is this inequality? This is the average of the logs. Yes. Average of the logs is? Oh. Yeah, so this is greater than or equal to the log of the average. So I'm okay. Yeah. So r minus 1 log of the average. I don't know why I keep getting confused with summation over V. Should I write 1 over n d bar here? This is the log, yeah, of the average. Average means this probability will have to be multiplied by degree V and summed. And that's what I have done. Is it, am I okay? Sorry. Yeah. This was average of the log of some quantities. I'm writing log of the average. The average means this probability has to be multiplied by this quantity and summed. Okay. That's what I've done. Sorry, people are not convinced. Is it okay or should I do it? It's okay? All right. Yeah. So you see this quantity, summation 1 upon n degree of V squared, yes? Minus, so this is Cauchy-Schwarz basically. So there is a d bar, I will come to that, but 1 over n degree of V squared. This is just a side remark. You agree that this is greater than or equal to 0? Because this is the same as, this is the average degree. Do you recognize this as the variance of the degree? And variance is always greater than or equal to 0. Yeah. So this quantity is always greater than this. So I can replace 1 over n degree V squared by this quantity. Yeah. So I get greater than or equal to h of V0, V1 plus r minus 1 log. Yep, please keep me honest. And this, yeah, so I'm going to replace this, which appears here, with this. This is the average degree, that is d bar. D bar. Yeah. sorry, this n was, this n was gone. We're almost there. This is equal to h of V0, V1 plus R minus 1 log of d bar. Yeah. Okay, all right. So how far are we from what we really want? Yeah, so we seem to have got d bar to the power R minus 1 because there are logs involved, we will, yeah. Except we are, now, what is V0, V1? Yeah, so actually Sanjib already told us how to calculate that. V0 is a vertex picked according to the stationary distribution, and then this is V1. What is the probability that, yeah, you make this transition in the first step? So what's the probability that V0, V1 was this edge? This graph has many edges. Yeah. What's the probability that you make this transition in the first step? Well, you must have landed here. Yeah. And then you would have had to make this. And we did that calculation with some cancer. Yes. 1 upon. Yeah. And this was the same thing as 1 upon. So actually, in the first step, each of these edges in both directions is being chosen uniformly at random. And when that happens, so if you look at the V0, V1 themselves, it is any edge in each of its two directions being picked uniformly at random. That means it is a random variable which is taking these possibilities, these many possibilities with uniform distribution. Then its entropy will be log of this number. So this is the log of that number. So this is log of n d bar plus R minus 1 log d bar log of n times d bar to the power. So, yeah, let us look at log of the number of walks is greater than or equal to log of n d bar to the power r. Cancel the logs and you get our inequality. Okay. So you see, yeah, so you see what happened. So we wanted to prove this. Vaguely felt that entropy might be involved, but we needed the right probability distribution. And in this case, it so turns out that if you use the stationary distribution of the underlying Markov chain, then the calculations become simpler. And where did the calculation become simpler? Because of the stationary distribution. Because there were these many terms, yeah, and they all became the same. Because we sort of chose to analyze this problem under the stationary distribution. Is that all right? So that was my second example. Sorry, please ask questions. People seem to be a little stunned. Yeah, I mean. That's right. So you're right. So you're talking about this consequence, that I'm able to write this. Yeah. The point is the distribution of Vi. Yeah. V0, V1, Vi minus 1, all these, because you are doing this random walk, where you came to Vi minus 1 doesn't matter. Your next step is determined only by where you are. Okay, so in that sense, it is the Markov property. And whether you condition on everybody or condition only on the last one, the distribution of Vi stays the same. And that is why only the last one, somewhere I should have written, yeah, only the last one matters. And it's the dig, yeah. You'll check this. Give you one more example. This is called Bregman's theorem. Yeah. I went over time last time, so I reminded me today. Yeah. So Bregman's theorem. So what is Bregman's theorem? You have a matrix, n cross n matrix, which consists of zeros and ones. Then there's something called the permanent of M. Okay, so this permanent of M is a cousin of the determinant. Yeah, and this is defined to be, I don't know how you write. Look at all permutations of 1 to n, and then I will give you a better definition, perhaps, yeah. So this matrix is this is an n cross n matrix. The ijth entry of it is Mij. Okay. And permanent of M is you try to pick numbers so that you shouldn't be picking the same number from two numbers from the same row or same column, and you just multiply them and you just add them up. Okay, in all possible ways that you can do this. So if you pick a 0, this product will become 0. Yeah. So you should just be picking ones. Okay. So this is closely related to determinant. The only thing missing is the sign of the permutation. Okay. Yeah. Now this is a very important object in computer science because it counts something which physicists ought also to be interested. So suppose you imagine that this was the adjacency matrix of a bipartite graph. That is, in position I, j, you write a 1 if vertex I here is connected to vertex j here. Okay. And what does permanent count? What is this? Yeah. So if you have such a matrix, well, each of these permutations, which gives you 1, means for in the first row it picked some item, which means then in the second row it picked something, but it's not allowed to pick the same thing. So and the permanent is the number of ways of matching the left-hand side to the right-hand side. So you're given this graph and you're asked, how many matchings does it have? Okay. Maybe you are familiar with covering it with dominoes. Is that, yeah, so you have some, yeah, so you are trying to cover this space using dominoes, but only certain things are feasible, others are not feasible. Yeah, so what does Bregman's theorem say? Yeah, so So this is vertex 1, vertex 2, vertex 3, vertex n. Each of them has a degree. Yeah. So right away, we can write permanent is less than. How many choices are there for the first vertex? If its degree is degree 1. Yeah. It has these many choices. Yeah. The second vertex can have how many choices? The last vertex can have, yeah. But it may be that having made this choice, some of the choices here are ruled out. This upper bound is paying no attention. Says so many choices for the first one, so many choices for the second one, so many choices. So the total number of choices is bounded by this. Okay. Bregman says, I can do better. Okay. Because if you look at this number, degree of I factorial to the power 1 over degree I, yes. And if you remember your studying formula, this is degree divided by, what does n factorial look like? Or k factorial looks like k, some lower order terms. And then if you do, yeah, this would have been k. Bregman has k over e. Yeah, that's the main power. It looks like a small improvement, but this has deep consequences in combinatorics. Okay. So where is the randomness? Yeah. So pick a matching uniformly at random. Yeah. So what do I mean? So this graph has many perfect matchings, perhaps. I'm picking one of them uniformly at random. Yeah. Okay. So suppose the number of, yeah. So how do I record that matching? I ask J1, J2, Jn. What do I mean by J1? Which vertex is vertex 1 match 2? That is J1. Which one is J2 match 2? Sorry, I2, vertex 2 match 2. That is J2. Vertex n is match to Jn, and I'm picking a uniform perfect matching uniformly at random. Okay. So the entropy of this is Is everybody okay? If you pick something uniformly at random from a certain set, its entropy is the log of that set, log of the cardinality of that set. Yeah, nothing. Now, we do what we do always. When you see a whole string of random variables, we expand them using conditional entropy. So we will look at h of J1, then h of J2 given J1, h of J3 given J, and so on. Okay. Now, here there is a twist. It turns out that these are some random variables. We want to expand them. In what order should we expand them? Okay. So now the trick is expand them in a random order. Okay. So meaning pick a permutation tau uniformly. That is, so in our, here is the graph and here is a matching. Okay. So first you pick a random vertex from here and ask, who are you matched to? Okay. That will reveal me that coordinate. Okay. Then I pick another vertex other than this. Yeah. So I first pick j of tau of 1, then I pick j of tau of 2, j of, yeah, so I reorder this like this, and then expand. H of j of tau of 1 plus h of j of tau of 2 given j of tau of 1. This quantity is equal to this quantity. Yeah, no matter. So I can just take an expectation here. The expectation is over the choice of the order. So let me again. We have picked a matching at random, and now we are interrogating the vertex. Who are you matched to? Who are you matched to? Who are you matched to? And each time we are going to account for how much information we get when the new vertex is asked a question. Yeah? So you ask a new vertex, which are you matched to? And it says, I'm matched to this. How much information did it give you? Okay. And we will be able to bound this nicely. Okay. That is the spirit of the proof. But the interrogation is being done in a random order. Okay. Yeah. Now, actually, there is only one step. Here is a vertex V. It has degree of V neighbors. Now, V's turn might come somewhere. It might be the first vertex to be interrogated, seventh vertex, sixth vertex, anything. Yeah. But when V is interrogated, how many of these guys still survive? Yeah, that is the question. Because if only 4 of them survive, then the amount of information that we get is log of, at most log of 4. If only 1 survives, no information, because I knew that you have to be matched to that because the others have been taken by others. Okay. Now, the important thing is, look at any matching, and if you examine it in a random order, if there is a vertex here, W, which is matched to this, whether W comes before and W's neighborhood is like this. Sorry, W was matched to this. If W came before or after V, it doesn't matter. Because if W came before V and then we visited V, we would have been told that W is matched to this one. And as far as V is concerned, its neighborhood is still intact. Who are the vertices that we care about? Those vertices that are, one of them is V's, V is probably matched. These others are matched too. Yeah. And the question is, what is the position of V among these degree of V fellows? Because they are the ones who are going to deplete this. Now, if I take, K items, yeah, so you are standing, you are in a class of K people, and I arrange the K people in an arbitrary permutation. What is likely to be your position? You will be the first with probability 1 by K. You will be the second with probability 1 by K, third with probability 1 by K. So when V is examined, out of the degree V possibilities, it is equally likely that there is only one possible, one left, or two left, or three left, or four left, because it just depends on V's relative position among its competitors. Yeah. So the amount of information, so I'm writing an informal statement. Yeah. Yes. When I examine V, yeah, which means I'm looking at, yeah, when I examine V, I'm equally likely to have one neighbor left, two neighbors left, three neighbors left, or degree V neighbors left. If I have only one neighbor left, my entropy can be at most log 1. If I have only two neighbors left, my entropy can be at most log 2. And each of them happens with equal probability. So this is this. Now, if you see, this quantity is log of this is just, I'm saying that this degree V I take to the top. Yeah. So this quantity, if you believe my story, is bounded by summation over V, yeah, log of degree of V factorial to the power 1 over. Okay. So I did not explain this very carefully, but the spirit is this, that if you examine something in a random order, the number of neighbors that will survive when you examine a particular vertex is equally likely to be any number between 1 and degree of V. This is a little, you have to sort it out in your head. But once that is done, there is nothing left because everything is taken over by conditional entropy. Okay, and we get this rather powerful theorem out of it right away, because now there was a log somewhere. I wrote log of permanent is bounded by this. Now you remove the logs and you will get the product. Maybe I should stop. Yeah. Yes. It depends on the matrix. Yeah. Suppose it's a random matrix. 0, 1 matrix, yeah. Yeah. So it gets close to this. Yeah. Yeah. So I don't know how fast, but yeah. But this is a kind of it's not for a random matrix, for every matrix M, where the ith row has di ones, degree of I ones. Yeah. Number of ones in a row is the same as the degree of the vertex here. Yeah, so when this, so for example, suppose it was a complete graph. Yes. In that case, so if this matrix was all ones, then what is this quantity? If it's a complete graph. This graph is a complete graph. Everybody is connected to everybody. Then what is permanent? What's the permanent? How many ways are there to match this to this? If everything is allowed. How many ways are there? How many possible ways are there? So what to match this to this? N factorial. Yeah. So all these numbers, each of these degrees would be n. You would get n factorial to the power 1 upon n, but you will multiply them n times, so you will get n factorial. So yeah, product is 1 for every permutation sigma. Yes, so this summation is over n factorial always, but in the happy case where everybody is 1, each of these summands is 1, so you get n factorial. That is one way to see this. You can also see this. Yeah, so I don't know how useful all this was, but sometimes you might feel that you can optimize this and there is some concavity, some convexity going on. I think it's a good idea to see if, after all, the problem is information theoretic. Okay, and I've shown you 3 examples where adopting an information theoretic mentality, yeah, helps. There is creativity involved. Yeah, you choose the stationary distribution. Here you choose to examine it in a random order. Yeah, not in any deterministic order. Choose to examine it in random order and compute the expected value. Okay. Yeah. So, questions? Okay, so this was sort of application of information theory. Tomorrow we will get back to some more theory. There is this important thing called relative entropy, which I hinted at, and it has connections to statistics. So we will do some relative entropy, properties of relative entropy, and what it has to say about statistics. Sorry? No, yeah. So that is the paradoxical thing. It looks like permanent is an easy function. All those nasty minus ones are not there. But actually, we don't know any way to compute a permanent, any fast algorithm for computing the permanent. For determinant, how do you compute the determinant? Suppose I give you a matrix, how does one compute the determinant? What's a good algorithm to compute the determinant? Sorry? How do you compute the determinant? What is? Sorry? Oh, how do you compute the eigenvalue? No, that's probably too hard for me. Yeah, how do you compute the determinant of a matrix? Yeah, so you do Gaussian elimination. Yeah, so you do row operations on a matrix so that you have, it either becomes upper triangular and then multiply it by. Both will be fine. The thing you should not do is Kramer's rule. Okay? Yeah, yeah. Because that takes n factorial time to compute the determinant of an n cross n matrix. And if you look at high school math classes on YouTube, everybody teaches you determinant, use Kramer's rule. They will, of course, do only 3 cross 3 matrices and declare that to be a great algorithm. Okay. So, yeah, as a computer scientist, it hurts me. Yeah. So, yeah, Gaussian elimination. Yeah. Thanks.